Thank you very much. Actually, the title should have been High Performance Flexible Electronics by Printing. So I was just struggling to find that extra space, but that's the title. And I'll explain in these slides our research related to high performance flexible electronics, particularly the printing technique that we are using for various high mobility materials. So flexible electronics that we are doing is over various dimensional scale. We start with nanowire, and we have developed skin for complete humanoid robot. I'll come to that. As well as on the time scale, some solutions which are already we developed and are available in market. Some are available in near term and some in long term. So for example, nanowire printing that I'll explain in the last part of my presentation is something that we look as a long-term solution. Off-the-shelf component on flexible printed circuit boards is something that we have already done. So I would start by acknowledging my group members. The work I'm presenting is something that they are working hard, and I'm quite thankful to them. So this is the outline of my talk. The first is the why high performance flexible electronics is needed. I'll give some examples. I'm sure previous speakers have also given many examples. My presentation is less about cost and more about the academic things. The second part is flexible electronics technologies, what various methods are available. I'll give a quick comparison of various materials, bendable systems from existing, which is kind of this thing is just on the basis of time scale. So this is from existing non-bendable technologies. Organic semiconductor, where I'll focus on graphene only because it's a high mobility material, and we print that also. We do transfer printing of graphene as well. And inorganic, where I'll focus on silicon. And I'll conclude then finally. So this is where we started working on flexible electronics. In this slide, various robotic hands and robot that you see, they have skin on them. So that's it's embedded here. In this case, also embedded. This is high resolution phosphor tactile sensing chip. That actually triggered the all flexible electronics research, because this was not planar, and I wanted to put it on the fingertips. So that's why flexible electronics started. Here, graphene-based skin was integrated, and this is off-the-shelf components on flexible printed circuit boards. Large area is also important, and because the body, if the electronic skin is something that we are working on, exploring, and our body has skin distributed all over the body. It's not like vision that you have two central points and everything is centered there. So large area is equally important, as well as multiple functionality to feel range of parameters, hot, cold, glossy surface, textured surface. So you need distributed electronics and high performance as well, because this type of task, robot has to act very quickly. It is sensing and acting. So, and the feedback, if you take into account, it must be fast, of the order of millisecond to execute a task. As well as these are some of the driving elements here, various applications where this kind of flexible electronics or electronic skin type of research can be used. And these are potential future scenarios where we can, if electronic skin is developed or high performance materials are sensors, electronics, a complete system is there, we can think of neural control of limb, avatar kind of applications, displays, interactive displays, etc. Wearable system is another application area where we talk about these days also, not just this one, but smart cities, IoT, all those applications where you are talking about the communication, fast communication, fast computation and communication both. So for example, in case of IoT, we are talking about 200 to 300 megahertz kind of switching frequencies of transistors, which is something goes to high performance again. It translates to that. Number of sensors around body. You want to transmit this data to mobile phone or other portable gadgets. High performance is pretty much needed. So in my group, we are working on various areas, silicon nanowire based printed electronics, graphene based devices, as well as some other materials we have explored, or primarily graphene, ultra thin chip, which is where compact electronics you can put and make the complete thing flexible. and some work on stretchability as well, because we want to integrate everything in one system. And stretchability gives that extra element. And what I mean by a complete system means multiple functionalities integrated on same substrate, possibly with wireless communication as well. So coming to the second part, materials and methods. So this slide gives a broadly categorizes these materials for flexible electronics. One is organic semiconductor, inorganic semiconductor. That's where most of the high performance lies because of high mobility. But high mobility is not the only criteria. It's the channel length, it's the other parameters such as ohmic junction, etc., which are also important. They all together define high performance. But typically, we start with mobility. And then here we have organic polymers, molecular compounds, etc. And graphene is something that has significantly attracted attention these days, but the technology is still not available. In terms of their suitability, depends on what we want to do. Certainly one application that I'm working on is robotics and prosthetics, so electronic skin for those areas where high performance is needed. But this slide gives on this axis you have mobility, on this axis you have transistor switching frequency. For example, these applications that we seed, you need, for example, for your computer screen refresh rate is about 70 hertz or 80 hertz. So that's the kind of response, and that's why OLED is pretty popular there. But if you are looking at applications that we talk about today, I said earlier, Internet of Things or smart cities, etc. We are talking about distributed sensors, distributed networks, wireless LANs, etc. All these areas would require switching frequency, transistor switching frequency in the megahertz order. And that roughly translates to high performance in terms of high mobility. So that's why high performance and high mobility material, they come together. And people have started looking into various materials. This slide gives a complete comparison. On this, you have various attributes that we look for generally from electronics engineering or from device fabrication point of view. Organics, graphene, silicon in various forms, and group 2,6 materials coming here. So that's the first parameter that we start with, mobility. In case of organic, it is 1. In case of single crystal silicon, it is 1000. So 3 order of magnitude difference. So if a transistor made of silicon is switching at 1 megahertz, this transistor will be switching at 1 kilohertz roughly. So this is pretty much restricted when you go to device. Best printer available, you can go up to channel length like 20 micrometer or so. And with this mobility frequency, switching frequency will be kind of 100 kilohertz roughly that you can come to. But this, if it is 100 kilohertz, that will be 100 megahertz. So that's the kind of the range we are talking about. Obviously, people say that here in this case, fabrication cost is low because you can develop this by printing, but the printing is not the only criteria for the cost. Eventually, you have to think of packaging, you have to think of lifetime, stability of device, etc., a number of other parameters, and silicon is very well tested on all these cases. Metal oxides have attracted attention recently, which is also an important, quite interesting area. But our focus remains here because the technology is quite mature. Silicon material is, you can get high purity material, and if you can milk more out of existing technology, this is ideal. So I'll go to the silicon and focus on silicon and graphene. So we started working on this. The first element was robotics needs tactile skin quickly and high performance one. What do we do? I cannot rely on nanowires and wait for 5 years and advanced research in other areas. So only solution that was available to us was we use off-the-shelf component, integrate them in such a way that we develop skin. And we got a European project funded, which is robust skin. This is iCup without skin, iCup with skin, and nicely packaged skin, which is now available commercially as well. And the concept was quite similar, simple, Fuller map concept. We wanted to develop a skin not just for iCup, but a general skin. Any curved surface we should be able to cover, and we start with the complex shape, which is a sphere, a globe. And the concept is In a fuller map concept, you take triangular projections and you make 2D layout. And if this 2D layout is available to you, now you can cover this 2D surface and rebuild the 3D surface again. What you get is a surface which is maximally covered with the skin. And that's what we did, and that also explains why we have triangular shape of the patches. Because triangulation technique is very well known for 3D imaging. Those in computer 3D imaging and computer computing, they know this, working in those areas, they know this very well. So we implemented that in hardware, and we were able to cover maximum area. Of course, this technology has a limitation. You cannot cover areas where curvature is small, such as fingertips or this kind of area. But on large areas where curvature was big, we were able to cover it, and it led to changed the paradigm in robotics as well. Before the skin, robotics research was focused on manipulating objects with hands, sometimes with 1 or 2 touch sensors and sometimes without touch sensors. But it led to the change because whole body contact was used after this, and many projects were funded by European Commission after this. I mean, consider an example. You want to lift a heavy sand bag. You are not using any finger there. You are just grabbing it and picking and placing somewhere wherever you want to. And the contact from simultaneous contact, from area contact, from large body parts, they come into picture at that time. So we were lucky that at that time the iPhone came with this chip capacitance to digital converter. This chip was 87147, and there were 12 capacitors were converted into digital values. So we used that chip, we integrated it on the back side. That's also explained why we have 12 sensing elements on the top side. Wiring complexity is one major problem in robotics. For this kind of application, you want to make intelligent routing mechanism and want to reduce number of wires, because as number of sensors increase, number of wire will increase, and if you want to put this type of skin on a dexterous hand, so dexterity is sacrificed. So that does not serve the purpose. So this was another challenge that was resolved here. So this is the top side, the back side, and this is triangulation technique which is shown here. These were all capacitive sensors, and it was implemented on different type of robot just to show that it was a generic skin. So that's the iCub. This is Casper, which is a robot. It's a research robot used for autistic children, commercial robot now, and shrunk robotic arm, which is in automation sector. And this is what I explained, what led to change in the research paradigm. So you can see the skin is on the body, and area contact or single contact point, these are the activated points. So after that, people started also looking into touch, vision, coordination, etc. Before this, it was not possible. Coming to this next point, we started working on other areas. Capacitance has a problem, traditional capacitive sensors. So we also started looking into what other materials could be used, and the printing started coming at this point. So we developed, the first was to develop, we started looking into graphene, but graphene we know is normally available in small patches, commercially also available in large area. So we synthesized graphene on copper and transferred it on the quite large area, which is 25 centimeter by 25 centimeter, and the results were quite nice. And we wanted to, we did it on a highly polished copper, not the commercial highly polished copper. This is the commercial one. We just took copper, which is used in lithium-ion batteries. Because of chemical reaction, it is much smoother than what you get highly polished. So when you go to nanoscale, even highly polished will have these lines that you see here. But because graphene is single atomic layer, these lines that you see here, when you are transfer this graphene on flexible substrate, they become crack. So there is no conformal contact between two surfaces. Whereas in this case, we noticed that there was no crack. This is the device made from the cracked one. That's how you see the crack. And this is the device made from this graphene, and we noticed that device eventually transistor performance was better in this case, which is obviously because of the crack, the performance goes down. So we extended this work to develop our next skin, And this is the fabrication process. This is the transfer process. You have graphene on copper here. This is the flexible substrate we want to transfer, and this is a hot lamination method. So basically you are laminating it. So on PVC you have graphene, and then on the back side you just etch away copper. What you get is graphene on PVC then. And now after that, once it is there, we do not use lithography, because lithography is known to damage graphene. So what we did, we simply use blade cutting tool. Yes, this is about 30 micrometer. There are other tools available. So that's how we got, and the performance we got in terms of sensors was much higher than similar sensors obtained with other metals such as gold. In this case it is gold. We extended it further. Graphene is transparent. There was some questions about energy a while ago. Skin also needs a lot of energy. Number of sensors you increase, energy requirement also increase. So what we did, we took advantage of graphene transparency of the skin. We integrated the skin with solar cells, and the combination became energy autonomous skin. So the transparent graphene allows light to pass through the structure, and solar cell was generating. We intentionally picked up a low efficiency solar cell, and we demonstrated. This is red color that you see is the output, power output without skin, and green is with skin. That means 2% light that is not going through graphene is not creating a big difference, big drop in terms of power. And graphene is the skin needs 20 nanowatt per centimeter square. So you can translate it into the complete body if the skin goes on the entire robot, the kind of power we are looking at. So basically we were producing more than what we needed for this application. For other applications, obviously requirements will be different. There was no transparent skin before that, so people never tried photovoltaic. So that was a change here. And these are some videos which show results of this skin. We placed this skin on this prosthetic hand, which is iLimb from Touch Bionics, and this is without skin, enabling skin. It squeezes the soft object, and when you enable the skin, it stops at a point. So the skin was quite sensitive. These are output coming from various phalanges here. And number of areas where this can extend is given here. We also further extended it, brought back our previous experience from using off-the-shelf components. We integrated off-the-shelf component on the back side of flexible solar cell, and on the top side was still the skin, and that's what you get as a complete thing. We were able to do it again. Now coming to inorganic, we started, as I mentioned, ultra thin chip work. We came up with this nice process, which is chemical etching of wafer scale, chemical etching and getting ultra thin chip. This is new technology that we developed, and the silicon in this case is 15 micrometer thick, 1.5. The conventional grinding technique leads to about 50 micrometer, 50 to 70 micrometer, but in this case we were able to get the wafer scale process, and that's the kind of bendability you get with silicon. So with 15 micrometer, this is 2 centimeter long and 1.5 centimeter wide. So this is without any substrate. On this we have silicon is on PDMS. Substrate also affects the degree of bendability of silicon. The problem with the ultra thin chip kind of approach is that you can have a compact electronics but in a small area, whereas for the skin kind of applications we need electronics on large area, and this again brings me back to the printing. In previous case also transfer printing was involved. So we got we thinned the wafer, and using the same transfer printing that I will explain in next slide, we were able to transfer ultra thin chips on flexible substrates. I'll just conclude it quickly. So this was the first approach that we started. This is something that came with John Rogers' group. He developed this technique with top-down approach. We are not using top-down in the same sense, but this slide explains the concept. You realize wires on wafer, you transfer using PDMS. One transfer, these wires are transferred to PDMS, but because the metal contacts are on the top side, at the interface of PDMS and wire, we need to transfer them again. So then after that, you can print metal lines, etc., and you get your device. So in this case, PDMS is on the wires are on PDMS. These are transferred back to polyimide. There's a very high yield that we got, and then you get device out of this. So here, and you can repeat this process in a particular fashion defined by your layout, and you can transfer wires only where they are needed. So that leads to the electronic layer, formation of electronic layers, or very thin slice of wafer that you typically use for flexible, for normal electronics. And then you can carry out rest of the steps such as metallization, etc. So all high temperature steps are carried out when the wires are still on wafer, and low temperature steps are carried out after they are transferred. That's how you take care of the thermal issues as well. This gives us some device that we got with this approach. We are now extended this approach to get ultra thin, highly flexible skin. So these are nanowires. One textile is shown here. These are the nanowires, and they are connected. This is drain. This is the pressure sensitive rubber, so it is connected in this configuration. So whenever you press this one, this resistance changes, and there is a modulation of the current in the channel, and that's how we take advantage. So this is all integrated. We are quite in advanced stage as far as this work is concerned. So this shows the scheme. You have TFTs connected to PSR, pressure sensitive rubber, etc., or it could be a capacitive piezoelectric polymer or capacitor as a resistive element like that. So these are various configurations that we have tried, and this is supported by EPSRC. My fellowship project is focusing on this aspect, printing silicon nanowires to get electronic skin. This explains what we do in terms of printing. As I said, we don't use printing as I explained. We use metal assisted chemical etching because this allows us a good control on doping of wires, and we have also overcome the issues related to ohmic junction, etc. So you get nanowires. We synthesize both zinc oxide as well as silicon nanowire. This was basically to optimize the printing process, the custom printing setup that we have developed in my lab for transferring silicon nanowires on flexible substrates. So these are quite good nanowires. We are able to get about 20 nanometer diameter also, and transfer printing, and then you get flexible electronics. And we also developed this nice method of getting a self-assembled silicon, the micro nanospheres, which allow us to have a good control over the metal assisted chemical etched wires. So these are all top surface that you see, and we were able to get wires that were shown in the previous slide. So that's the process you get with silica spheres. You pattern it, and after in H2O to HF bath, you get wires, and that's the kind of wire you get. This explains the bottom-up approach, and this explains the top-down approach. That's just the difference between them. We are now, as I said, we have, I'll just stop it after this. This is, I think, the last slide that we have. I think this is quite important to explain the printing process. So we have developed this setup which allows us to print from silicon wafer, print directly to flexible substrate. So what we do here is we have two surfaces. This is the donor substrate. This is a receiver substrate. So receiver substrate is still on flat, but after that you peel it off and wires are transferred. So these are pressure is controlled with the load cell. So when you bring them together, there's a pressure also plays its role. So you define sticky areas on the receiver substrate. Sticky area is the area where wires are to be transferred, and non-sticky are they don't transfer there. These are defined by your layout. So you bring them together, and then you just slide the other side. So after that, you notice the results that are shown here. These are the wires transferred over different scales, and they are nicely transferred along the direction of sliding. So alignment is very important when it comes to device fabrication. That's why it is an important result. And first device we made was array of zinc oxide based nanowires at 4 areas, and this was used for variable dosimetry. This is the same thing, and I'll skip this part because this is not directly relevant here. We are also working on some same approach, extending it to neural nanowire, FETs, etc. And that's the new part, next part that we are currently looking at. We demonstrated the working of neural nanowire FET-based skin using simulation and we were able to get multiple parameters. So finally, this brings me to the end of the presentation conclusions. High performance flexible electronics is needed for emerging applications such as social robotics, bionics, Internet of Things, smart cities, etc. But that does not mean that this is the only solution. It is complementary to organic-based electronics. And one example is displays where you have OLED display, but at the back side you have drive electronics, which is high performance. If you want a complete bendable system, both together should be bendable, and that's how they complement each other. Flexible electronics, as previous speakers have also pointed out, various areas they have applications they pointed out. It's a disruptive area that will add new dimension to largely Moore's law-based electronics industry that we have today. With that, I would thank you very much.